Welcome. In this session, we are going to evaluate radioactivity and radioactive particles. To begin with, we are going to look at how the different radioactive particles are displaced within the electromagnetic spectrum. Welcome. There are three main radioactive particles, namely the alpha, the beta, and gamma rays. The alpha particles, being positively charged, are normally attracted towards the negative terminal, and since they are of low intensity, they are easily stopped by a thin sheet of paper. 2. The beta particles are negatively charged. Thereon, they are attracted towards the positive terminal, and since they are moving at relatively medium intensity, they penetrate the thin sheet of paper but are stopped by the aluminium foil. The third is the gamma rays, which are light, a form of light, and these rays of light move at very high intensities. They pass and penetrate a thin sheet of paper, they pass and penetrate a thin sheet of aluminium, and are only blocked by the lead block. In this case, this is a clear representation of how radioactive particles move within an electromagnetic spectrum. 2. I want us to study each of them independently, beginning with the alpha particle. The alpha particle is represented by the symbol seen there as an epsilon. 1. The alpha particle is a charged helium ion, and in this case, helium is normally stable, but during radioactivity, it is spontaneously discharged as a helium ion, which is positively charged. Number 2, it is deflected or deflects to the negative terminal. Number 3, as I said earlier, it has a low penetration intensity, which we could say penetration power. Number 4, given its property of mass number being 4 and atomic number being 2, whenever the helium particle is radiated, it causes a change in the mass number by 4 and atomic number by 2. So it changes mass and atomic numbers in the ratio 4:2. And number 5, it is stoppable by a thin sheet of paper. Simply because of its low intensity. Number 2, I would want to illustrate briefly what happens when an alpha particle is emitted. So basically, assuming that we have uranium-238, atomic number 92, and it so happens to emit an alpha particle. If it emits the alpha particle is represented by the helium ion, which is charged, and in this case, the process emits some energy. And as it emits the energy, we find that the mass number is reduced, uranium to 234 and 90, signifying that actually what has happened is a mass number of 4 has been lost and atomic number of 2 has been reduced. So that is a representation of what happens during the alpha emission. Number 2, let's look at the beta particle. The beta particle so represented is a free moving electron from the nucleus of an atom. So number one, it is a free electron from the nucleus, and normally it's represented by that symbol. Number two, the alpha particle is deflected to the positive terminal, This is simply because it is negatively charged. Number three, it has a medium penetrating power. You could say moderate penetrating power. Number four, it is toppable by the aluminum foil. And number five, when emitted, it causes a rise in atomic number by 1. Causes rise in atomic number by 1. Let's look at this briefly. So, assuming again we have the uranium-238. Uranium-238 has atomic number 92. If it so happens to emit the beta particle, what happens is that the uranium has a sustained mass, 238, but the atomic number rises by 3 to 93, which is a rise by 1. And here we have the beta particle represented as having been emitted. Why then is this the case? As alluded to earlier, the beta particle is an emission of a neutron from the nucleus of an atom, as represented here. So when the neutron is bombarded by an external force, you can call it a bombarding force, the neutron may be forced out of the nucleus. When that happens, it changes its form into a proton and an electron. The electron from the nucleus will be referred to as the beta particle. Now, since protons are not stable outside the nucleus, the neutron which has converted into a proton will be returned back into the nucleus. In this case, the net result of a beta particle emission is a rise in atomic number by 1, represented by the proton which are formed from the neutron. And that is why you can see that we had 92 protons, but at the end we have 93 protons, represented by the emission of the beta particle, and in this case the proton which has been formed from the discharged neutron. Next, I would want us to look at, in a brief way also, what is referred to as the gamma ray. When you look at the gamma ray, as I say, these are rays of light moving at the speed of light. They are represented by an inverted epsilon. So they move at 3.0 times 10 to power 8 meters per second, which is basically the speed of light. So number one, the gamma rays are rays of light at speed of light. Number two, they are not deflected towards any side in the electromagnetic field. So they are not deflected in the electromagnetic field. Number 3, they have a high penetrating power. Number 4, they are stoppable by a lead block. And number 5, when they are emitted, they cause no change in mass and atomic number. So, as you can see, that is what we are referring to as the gamma ray emission. Let me just illustrate that the same way as I've done with the other two. So, assuming we still have the uranium-238 subscript 92, and this time we have the gamma ray. What will happen is that the uranium will remain as 238 and 92, but there will be some energy lost. So that is the nature of the gamma ray emission. If I remind you again of what we have done here, 238 and 92 are the nuclear properties of uranium. If it is a beta particle, we have said that there is a rise in atomic number by 1 in respect to a neutron changing to a proton and an electron, the proton are being retained in the nucleus. The mass number remains unchanged, and the beta is represented by a negatively charged electron. The same way we have the uranium-238 subscript 92, and when the alpha particle is emitted, what happens is that we have uranium 234 subscript 90. That shows a clear reduction in the mass number by 4 and atomic number by 2 in respect to the alpha particle carrying the mass 4 and atomic number 2, as represented by the charged helium ion. Thank you. That is a representation of electromagnetic emissions. A reminder again of what happens up here is, as you saw earlier, the alpha particle being positively charged moves towards the negative terminal. Since it has low penetrating power, it is stopped by the thin sheet of paper. 2, the beta particle has a moderate penetrating power. It goes past the thin sheet of paper. It is deflected towards the positive terminal, and it is stopped by the aluminum foil. Number 3, the gamma ray is uncharged, neither positive nor negative, and therefore it does not deflect either to the positive or negative terminal. It has high penetrating power. It goes past the thin sheet of paper, past the aluminum foil, but is stopped by the lead block. Within a nuclear industry, what happens is that we need to have a nuclear reactor, a compartment which is inbuilt with a lead block, because the lead block is the ultimate stopping agent for all radiations. Thank you, and prepare to look at the next clip.